Hello, everyone. Welcome to Quantum Machines Talk at EQTC. And we wanted to focus this discussion around the control of quantum processor based on neutral atoms. So I'm Ramon Szmuk. I'm an atomic physicist by training, and I'm the product manager for all the AMO-based QPUs at Quantum Machine. So before we delve into the businesses, there's going to be a few slides of fluff about us and in general before we delve deep into the details of what it is that we do. So let me show you a bit who we are. So we are a company made with the DNA of physicists and engineers. We're currently more than 60 people, almost 70. And we were founded in 2018, mid-2018, with a mission to revolutionize the way people do control of quantum processors, quantum information systems, whether it be small laboratories doing experiments on prototype processors, or startups or large scalers that wish to produce production-grade processors. So we are exclusively focused on this, on quantum control for quantum information processing. And we have developed what we believe is the most advanced control system for quantum processors in the world today. And we will, of course, delve into the details of what exactly that means. And in particular, how does that look like for AMO processors, for neutral atoms in particular. We already have some traction, so we have customers in more than 55 customers in more than 15 countries. And the logos you see here are from academic institutions, because we can share mostly the industrial partners that we're working with, but we are. So we have large multinationals as customers, as well as many, many startups. And several startups and academic laboratories working with neutral atom processors. So what I'm going to show you today stems from the interaction with these researchers and working on real systems. We raised also quite a nice amount of money, so we're here to stay. Basically, we have a long-term vision to make a control system for quantum processor that is future-proof, quantum error correction enabled, and so on. So we have a long road ahead of us, but we have what it takes, we believe, to succeed. So one more slide about the people. I should have asked for a newer one. There are more physicists currently at QM than this slide shows, but basically, at least this conveys the idea that we are a bunch of quantum physicists and engineers with a multidisciplinary set of experiences. So some people come from, like me, from AMO labs, neutral atoms or ions. Some people in the company have background in superconducting qubits or quantum dots, envy centers. And as you will understand slowly as we advance, our control system is agnostic to the type of qubit. And so that's why we've assembled a team of people with a variety of experience in different kinds of quantum processors. So as I said, we have clients and customers working in most quantum, I don't want to say all because it's a big world, it's a big jungle, but most quantum processing architectures. So we definitely have customers working with superconducting qubits and spin qubits, atom arrays, ions, envy centers, and then subcategories of these. But we're here to talk about Twizzler arrays. And of course, because I'm leading a product for AMO processors, I have a particular, I like atom arrays in particular because of the advantages they propose. This is a very recent image, a GIF that was released by Quera Computing and Harvard just last month, showing the new 256 qubits simulator, currently only a simulator. It seems like in the literature these days, so atom arrays, for some reason, I don't exactly understand why, don't get the public relations that other quantum processors are getting, like superconducting or ion-based mainly. This probably has to do with the fact that the superconducting and ion platforms are being promoted by very large corporations. But I believe personally that neutron atoms really have more than a fighting chance. They are serious competitors. And the reason I think so is, well, first of all, they're highly scalable. I think out of all platforms, they are the easiest to, well, it's the easiest to envision a world with multi thousands of qubits, right? So superconducting qubits, you have roadmaps by IBM or Google or others reaching into the thousands and beyond. But other than that, smaller players typically are not that ambitious. In Rydberg arrays, the 1,000 qubit milestone is shared also among, with startups. So Quera said that they're aiming to have a 1,000 qubit processor within 2-3 years. Other startups like Pascal, I believe, have shared similar milestones. Also academic laboratories, which are typically not perceived as scalers in other architectures, in superconducting qubits, an academic laboratory typically works with a few qubits to do fundamental research. There are very few labs that are really looking to scale in an academic setting. In Rydberg arrays, we don't see that. We see that the ambition of academic partners is as big as the industrial ones. And everyone seems to kind of agree that we will probably have something on the order of 1,000 or more qubits within the next 2-3 years. And so this is really comparable with the most aggressive roadmaps for superconducting qubits. And I think there's a good reason for that. I mean, as this funny Mario Bros animated GIF shows, this here, by the way, is a 20 by 20 array. It's 400 qubits. It seems like it's relatively straightforward to scale. High fidelity and fast single and 2 qubit gates have been demonstrated, not necessarily on large arrays, of course. This is a milestone, it's a challenge still, but it was demonstrated that high fidelity operations can be performed in gate times under 100 nanoseconds. And so it looks like the community now is converging towards doing gates on this time scale. Some people are a bit more conservative and they prefer to have things a bit slower, say several hundreds nanoseconds. But in any case, several orders of magnitude shorter than the other relevant time scales, which are the coherence time of these Rydberg atoms or the atomic states used to encode memory, and even of the Rydberg lifetime, which is another important limiting factor here, which is, so the Rydberg lifetime is typically on the order of 100 microseconds or so. So, so it seems totally plausible that we will be able to squeeze many hundreds of gates in a single iteration of the experiment, and that is a very deep circuit by any standard, right? So currently, superconducting qubits, they are stuck below 20. With a quantum volume, log 2 of the quantum volume below 20. Another advantage of Rydberg arrays is the availability of multi-qubit gates. So for multi-qubits, I mean n bigger than 2. So there have been demonstrations and planning and plans for like C0 to the power of 8 or 24 even, for making, because of the long range interaction of the Rydberg atoms, generating entanglement in one shot, or using by addressing multiple qubits on smaller grids of arrays. And that will allow to quickly build up entanglement, which is, it kind of affords a shortcut to high quantum volume, right? If today with superconducting circuits, ions they also have a similar advantage, but if today in superconducting qubits you need to generate a sequence of 2-qubit gates to kind of propagate the entanglement causality cone, or however you want to call it, by doing multi-qubit gates on 9 qubits or 25 qubits, we'll be able to build up this entanglement in much less time steps, and so eventually and effectively will translate into a higher quantum volume if transpiling and compiling efforts will allow to seamlessly kind of transpile circuits into circuits that are using these more efficient entanglement generation gates. So this is, I think, is very cool to reach this, to aim for this milestone of quantum advantage. And there is also relatively recently, I believe, a scalable path to quantum error correction, even. Although the T2 of hyperfine states in atoms can be tens of milliseconds or even minutes. There's still a need to detect errors on the long term, and work towards a fault tolerant future. And I think so. Some people are working on this in private and have ideas, but there's already at least this publication by the Michel Looking group that seems quite promising and seems to be favorably scalable with the number of qubits. So, but it's to be seen. It's a bit into the future, but I think atom arrays have all the ingredients required to be a leading, or maybe the leading platform within a few years, at least as far as NISQ processors go. One negative point of Rydberg arrays is that it's certainly the slowest quantum processor in terms of clock speed. So most, I want to say all Rydberg array processors that I've seen, prototypes or not, are all working with a duty cycle, with a shot-to-shot duty cycle, which is below 10 Hertz. And so this is orders of magnitude slower than the second slower platform, which is ions, which typically can do repetitions of kilohertz or close to. Superconducting qubits and spin qubits, of course, are much faster. So this is an issue. It's not by no means a killer, but having your clock, your quantum processor run at 2 or 3 Hertz means that shots are expensive, and thought needs to be put into ways of optimizing the resource, which is the assembly of the array. We'll go into the details, into some details later on, into ways to kind of try at least to add some scaling, some prefactor to the clock speed by reusing atoms, and at least interlacing calibrations within the shot-to-shot operation. But this is not a negligible problem, but it's not a killer by any means. So the message of this talk, of this whole session, is that if you only bring us or fabricate a quantum processor, all the control stack and all the software can be executed today on one of our systems. So I've asked yesterday evening from someone in the lab to take a picture of the largest system that we're currently shipping to a customer this week. I was hoping it would be a 6 OPX, 6 device system, but what we currently have in the lab is only 5, but we're building even larger than that. And so the message is that if you buy one or more of these boxes, and that I will go into great detail, explain to you what they do, you today can connect your Rydberg array experiment and perform all the necessary control operations required to successfully run a quantum circuit on a Rydberg based processor and immediately have it accessible, on the cloud, and with us, you will be able to have a robust platform. So the point of all this talk is to convince you that these boxes are up to the task, and we will define the task in a moment. So yeah, there is this commercial, from Mares that makes scuba diving equipment that says just add water, right? So for us, just add atoms, and by atoms, I mean all the QPU, right? We don't make lasers, we don't make vacuum chambers, we just make control systems. And the centerpiece of our control platform is the OPX, which you see here in the picture, which has 10 analog outputs and 10 digital outputs and 2 analog inputs. To this box, you can add many extension modules. So we have digital input modules. We will introduce, I will show a brief slide on that, camera interface modules, photodiode detector, single photon detector modules, so that you can interface the system to all the basically readout equipment that you're currently using in your lab. We also have up conversion and down conversion modules that allow you to reach up to 18 gigahertz if you're doing microwave stuff. Yeah, so basically a collection of such boxes plus all the ancilla instruments that we will also provide is all you need to start producing production grade quantum processor based on Rydberg arrays or any kind of quantum processor that you'd like to make. So, okay, let's get a bit more into the details. Okay. So what does it really mean to, what are the requirements for driving, the control requirements for driving a Rydberg-based processor? So first of all, you have all the bread and butter atomic physics manipulations that everyone is doing today, the simple sequences to generate a mode, a molasses, maybe a 2D mode. You need repumper frequencies, you need cooling, you need optical pumping maybe. Maybe you have some microwave or RF antenna there somewhere, and you need to sweep some frequency. So, but in general, control pulses, AC signals, sometimes DC, but all on a time scale of several milliseconds, right? And this is basically the bottleneck for the clock rate of Rydberg arrays. It's all this, or at least part of it is all this laser cooling and trapping and preparation of the atoms. Because one issue with atoms, which is somewhat true also for ions, but mainly for atoms, is that for every shot of the quantum processor, you need to reassemble, the quantum array and reinstantiate it. So the first part of that is to prepare a reservoir of qubits in the form of a MOT or molasses or something that can later be loaded into the trap array. So and these are operations on a millisecond scale. We've been managing to do this for years now. There isn't really anything very complicated here. You can manage to do this with a DDS or any other sequencing hardware platform that are out there. And I want to convince you in a moment that the first part of this presentation, where I will show the basic building blocks of the quantum orchestration platform, I hope will convince you that these things are trivial to perform on our platforms. Then another thing you need to do after you prepare this reservoir of qubits is to instantiate the array. And by that, I mean to assemble the qubits, the atoms, into an addressable array. So an array of 16 by 16 for a 256 qubit array, or 32 by 32 for a 1024 qubit array. And you need to be able to then perform individual addressing of the qubits, right? Unless you're building a simulator, which is also interesting. But this addressability is an important issue. And so this can also be done with the quantum orchestration platform. Now this starts to be a bit more complicated. We are still kind of on the millisecond or high microsecond time scale here. But the issue is that these pulses that need to be generated to do atom arrangement, assembly, and addressing are typically multi-tone pulses, so composed of a composite spectrum made of many tones, that each of them corresponding to a tweezer that picks up and places atoms on the array and effectuates kind of the assembly of qubits. So I will show an example, a real live example, or half live, of how we do atom assembly, at least kind of the atom assembly 101. Then there's more advanced code out there that we've done, but I bought today, I'll show today just basic example of how you will do that. So instantiation is an issue. Oops. And then your control system needs to be able to perform, of course, the reason why we're here, coherent gate operations. And here we're going down to the nanosecond, microsecond, maybe millisecond time scale for very esoteric adiabatic pulses, maybe. But typically on the order of gates are typically on the order of several tens of nanoseconds. And so here, it's typically not very complicated spectrally. It's not typically doesn't involve multi-tone pulses, but here there is a requirement to have all the pulses generated on a multi-channel system in a phase coherent manner, channel-to-channel coherence, intra-channel coherence, preserving the phase of pulses from gate to gate, and from channel to channel. So you need to be able to reset the state of your qubits, perform single and multi-qubit operation, and in general be able to apply a universal set of gates to your atoms, right? So you need to be able to generate them, adapt the gates, optimize them. You need to take care of crosstalk between adjacent atoms. This is a challenge, and it requires a control system that is able to maintain phase and timing and stability across many gate operations. And then at the end, you need to perform readout. You need to read out the state, but not only the state. It's not readout here is put in a general sense. It's not only the quantum state that is read out in a quantum processor. You also have photodiodes to use to stabilize lasers, single photon detectors to do some kinds of readout. Some other, or many are using cameras. There are some esoteric readout that is done with RF or microwave demodulations, which is more typically found in superconducting and spin qubits, but microwave does find its way into AMO at times. And I hope I will convince you that also readout is very straightforward to perform. with the quantum orchestration platform. And I will show an example, not of a readout from cameras. I will briefly discuss our camera interface module that we're currently working on. I will show examples of readout using photodiodes to kind of bring a different, open your mind to different kinds of feedback that you will probably need to do as you go and generate a robust work towards generating a robust quantum processor. So readout is not just in the sense of reading out a quantum state. There's also many classical parameters that needs to be read out and stabilized. And so these are maybe the 4 basic operations. But so my background is in atomic physics, and then I worked for several years at MUCONS, which makes quantum sensors. So my first professional experience was in quantum sensing in metrology, time and frequency metrology. And it's clear to me, at least, that quantum computing is now kind of maturing and evolving to be a kind of a field of metrology, right? Everyone was very happy making 1.9 fidelity gates in the early days, 5 years ago or more. But now it's really about scaling and making this really work and solving useful problem. The holy grail today is quantum advantage. And we're no longer trying to simply publish a Nature paper, which is very nice and worthwhile, but we're trying to build robust systems that operate continuously with minimal intervention. And so the characterization, the stabilization, and the optimization of all the parameters that are associated with these 4 kind of sections of control for readable QPUs needs to be performed, and then the time scale crosses multiple orders of magnitude. So laser cooling and trapping, you might want to stabilize with a PID some laser intensity, or cancel some vibration or something like that. And typically this is done shot to shot. So on a second time scale, or several hundreds of millisecond time scales, so something that you could do, with a PC, but still it's something that needs to be performed. Then in the instantiation, you want to control and homogenize the trap frequencies of the atoms that are in the trap, the position of each atom, because this is how you're controlling kind of the interaction strength between neighboring atoms. So these are all parameters. The AOD's response, transfer function, and these things, drift with temperature, drift with laser intensity, drift with vibrations, misalignment, and in order to to generate a platform that can reliably execute quantum circuits day in, day out, these things need to be tracked and locked and optimized. Then, of course, the gates themselves, and I will show an example of this later on, where I'll show you how you can stabilize a sequence of gates to mitigate laser fluctuation, laser intensity noise. And so here we start to have, we really need to start talking about doing feedback on the nanoseconds or hundreds of nanosecond time scale. So kind of the time scale of a single gate. And I believe it's going to be absolutely necessary moving forward, with the goal of having 4.9 fidelity or an infidelity of 10 to the minus 4. I mean, if you look at the error budgets today for any AMO gates in general, even for ions, laser intensity fluctuations and phase noise are the 2 leading sources of fluctuations in these noise budgets. And so making, having an objective to concatenate many dozens of gates, one needs to think about how you stabilize these gates shot to shot to account for laser fluctuations. And I will give a very rough example of how you could do that, how we do that with the quantum orchestration platform. And readout parameters as well. If you're doing acquisition with photodiodes, you could think about optimizing, acquiring the whole photodiode trace and doing some optimal demodulation or analysis of the signal instead of just looking at how the value that the photodiode arrives at, after saturating to some threshold, which is what is typically done in many cases today. The thing is that AMO laboratories are used to having sequencers that have a time step of 1 microsecond or so, and we're not used to thinking about the possibilities, the options that are available if we will start generating signals with time steps of 1 nanosecond or on the order of that. And so it allows for many, and acquiring signal with this kind of bandwidth, with this kind of sampling rate. This allows many advantages, and which I believe are really necessary for the scalability of the technology. Okay, so this is on top of everything, this characterization, stabilization, and optimization, and the word efficient here is important also. You can't have a calibration of your QPU take, an hour. In the end, the idea is to have such a quantum processor online for users to load jobs on, and if every hour you need to stop the machine for half an hour of tuning, this directly influences, reduces the quality of your offering, and we're not in a lab anymore. We're trying to do things that are robust. So things which would appear to be like nice to have, stabilizing the phase of something, the intensity, it's not really a nice to have, it's really necessary. And it's also necessary to have a control platform that allows you to generate such sequences, such robust sequences out of the box, and not having to spend years developing FPGA-based systems and so on. Okay, so let's maybe start with a short introduction to what exactly it is that we're doing and how we're doing that. And hopefully by the end of this section, you will be convinced that at least laser cooling and trapping is something that you will be able to perform. So the quantum orchestration platform is the following thing. So the objective, first of all, is for you to be able to run even the most advanced experiments and protocols on a variety of QPUs at any scale, right? So for Rydberg arrays, we are already supporting devices of many thousands of qubits. Not on a single box, you will need to buy a fuller system, but we can do it today. But more than that, to be able to perform these, to generate these sequences from a super intuitive programming language. And I think this is really the paradigm shift. Having low latency and accurate pulse generation from FPGA, it's been done, but it's always at a cost of having some development overhead that, if done properly, it takes years. And in an academic environment, we very often see systems that are either good enough for the laboratory, but then a student leaves, and the lab is left without a control stack, or something that is buggy and doesn't work, and then you start to lose trust in the measurements that you're taking, or you're not able to do everything you would like to do, or if you would, any reasonably small change that you want to incorporate takes weeks of recompiling. So the mission of quantum machines and what we're here to do is to basically give you FPGA or like performance, but programming interface that is Python-like, that is high level. So at the core, so we have in the boxes that you saw, we get analog outputs and digital outputs and analog inputs. We have an RF and microwave front end that allows you to send and receive signals, basically. So DACs, ADCs, and then up conversion and down conversion to reach microwave. And then at the center of everything that we do is what we call the pulse processor. So the pulse processor is a processor architecture, an instruction set that was developed by quantum machines. It's a new kind of instruction set that treats waveforms and signals as the core, as the main data set that it operates on. So the pulse processor runs sequences in real time and generates waveforms and analyzes waveforms on the fly in real time. And I will go into great detail, explain to you exactly what that means. The basic capabilities is the generation of waveforms, which is done parametrically. So for example, to generate a sinusoidal simple pulse with no envelope, it takes no memory. There is not an AWG. You just specify the frequency and the amplitude, and the pulse processor will generate this waveform on the fly in real time. If you supply a waveform, an envelope, then all you need to store in memory is just the envelopes, and then this will be up converted digitally to the frequency that you want to achieve in real time. So basically this Gaussian envelope you see here would be streamed out of the pulse processor, and as it exits, it will be modulated by 100 or 200 megahertz or whatever. These frequencies can be tuned. The phases are parametric. You can do full frequency modulation. You can do chirps, not only linear chirping, but any arbitrary frequency modulation, any arbitrary amplitude modulation. Phases can be tracked, and so on. So the waveform, the sampling rate can be changed, and even the port, the output port that the signal is coming out from can be changed in real time. So the pulse processor, firstly, is a very agile waveform generator that takes very little memory. I will convince you, I hope, later on of why that is, because the waveforms are generated on the fly. Then there is waveform and data acquisition in general and manipulation. So signals can be acquired by the pulse processor via the ADCs in the RF microwave frontend. Demodulated, integrated, treated in real time. We have you can either acquire the raw data and manipulate it yourself using QA, that I will show you in a moment, our programming language, or you can apply a series of different kinds of pre-made demodulation modules that we have inside the pulse processor that allows you, for example, to do time tagging, threshold detection, counting, photon counting, binning, and so on. And simple demodulation of signal, estimating the phase, IQ demodulation, and so on. And everything is done on the fly. And then you have real-time processing, so Turing complete processing. We have variables, integer, fixed point, booleans. We have vectors. We have vector operations, evaluation of trigonometric functions. Casting of different types to other types. We have a very kind of expansive math functionality and classical processing that is fully executed in real time with strict timing. So any mathematical operation that is executed on the pulse processor has a clear predetermined amount of clock cycle that it takes to perform. And so this allows you to generate sequences that produce quantum control of quantum pulses, or sending out of waveforms to quantum to qubits, and the processing, the classical processing, in a single sequence. So very interesting for things like VQE or any kind of processing that you want to perform in real time. And the last part is comprehensive control flow. So we have if then loops, for loops for each loop, while, switch case, any kind of control flow that you would expect to see in a high-level programming language. We have in our it is capable to be executed on the pulse processor. And so, yeah, the idea is that you write a sequence in a programming language that we call QA, our own programming language, which is open source, by the way. So you can already find publications online, where the authors are using our instruments and they're sharing QA code to do different kind of things. And so the QA code that you will write in a Python environment will be then compiled using our own compiler and stored in the pulse processor to be executed in real time. Yeah, so these four kind of operations are per channel, so per processor core. The pulse processor is a multi-core processor. The current iteration has 18 cores. And so you can generate waveforms and place them in time and do relative timing and control, the relative execution of pulses on different channels in a truly parallel way. And I will show you examples of how this is used to generate frequency multiplexing tones and everything that you will see. We are agnostic to the type of qubit, because in the end, if you really think about it, qubits are two or few level systems. So if you can properly generate and acquire waveforms and generate signals with a baseband of several hundreds of megahertz, you should be able to control any kind of quantum device. Now, of course, because what we're offering here is a full programming language, high-level programming language, then you can write your own sequence. You can you're not restricted to a closed set of operations that a manufacturer pre-compiled for you on the FPGA. You write your own instrument. I like to say we are not a laboratory instrument company. The quantum orchestration platform is a generator of laboratory instruments. Every QA program generates a sequence of pulses and analysis of returning pulses that is fully programmable, and so effectively allows you to generate a new instrument just by changing the QA code that is running on the pulse processor at a particular moment. So the pulse processor can be a vector network analyzer. In a simple example, it can be even a phase noise analyzer. It can be an AWG if you want, but it's more than that. It's everything that you can write, right? Within some constraints, of course, of the hardware, but I think I will convince you in a moment that these are not very big, certainly not for big arrays. So yeah, just to recap, so you write code in QA, it's hosted within Python, so I use PyCharm, it's compiled, your sequence is compiled, stored on the pulse processor, and then executed in real time on the OPX. So how does it work? So qua, you write code. So you have pulse level commands. As I said, the generation of the waveform. So the play command is maybe the central command in qua, where you send a pulse to what we call an element. This is qubit 1 xy. And the element is our front-end interface to physical objects in your lab, basically. You define an element as being an assembly of inputs and outputs going into a particular object in your lab. And it has a characteristic frequency. So if it's an AOM, for example, it has a characteristic frequency of typically in AMO, so 100 or 200 megahertz, a characteristic correction matrix if you're using a mixer. And so when you send a pulse to an element, the pulse itself is transformed to accommodate according to the characteristics of this element. So if, for example, I've stored in memory my pi pulse, let's say it was a Gaussian, and I play it to this element, to this qubit 1 element, and if this qubit 1 element is set to be 100 megahertz, let's say, then the Gaussian will be up converted to 100 megahertz. If I would now play this pi pulse to a different qubit, which is set to 200 megahertz, the same Gaussian waveform on the fly will be up converted to 200 megahertz. So there's a lot of reuse of baseband memory. Basically, if you're sending Gaussian pulses, you only need to store a few envelopes, and then the particular characteristics of this envelope are transformed on the fly in real time, depending on who the pulse is being played to. The measure command is the second, maybe most important command in qua, and that allows you to read out signals, basically, coming into the OPX. So readout is again a pulse. So any measurement in qua is typically associated with an excitation, but you don't have to. You can send nothing if you want. And then again, you send this to a particular element, and then you define also a time of flight, the time it takes, for the signal to go, the propagation delay through your lab until it comes back to the OPX, and then an acquisition window is opened, and you can either take the raw data, or you can integrate the signal, you can demodulate it, you can do time tagging, you can do sliced integration and save the result into a vector. There's a bunch of stuff you can do. Photon counting, and then the result of a measurement is stored into a qua variable, right? Which can then be used to do feedback or anything you'd like. So we have general variables and classical processing. So you can do arithmetic, of course, and things which are much more complicated than what you see here. So of course, addition, subtraction, multiplication, division. And as I said before, we also have a long list of trigonometric functions, log and exponents and vector operations. So finding the maximum or the minimum of a vector, the index of the maximum, what else? The sum of a vector, casting, and more, and the square root, and we're constantly adding more and more real-time mathematical evaluation of functions in real time. And so all these things are run, in real time on the pulse processor. And A and B, these qua variables, can be the result of measurements, or not necessarily. It can be any variable. Yes, and then these variables can be used to scale pulses. So if I want to play again this pi pulse to this element, this output port, if you want, you can scale the amplitude by a constant. And you can also stretch the envelope to a determined duration. So for example, you could just store the samples for a 100 nanosecond Gaussian. And then if you decide, mid-circuit that you want to actually make a 1 microsecond pulse, then you can change the duration of the pulse here, and the pulse processor will perform a third order Lagrange interpolation in real time on the envelope and output, a 1 microsecond signal. Of course, the carrier frequency inside will still be the 100 megahertz or whatever of this qubit. It's just the envelope that is stretched. Same goes for the amplitude. You can scale the amplitude as much as and it can be determined by a core variable. Yes, as you see here, this is a more complicated measurement command. So you can demodulate something, use particular integration weights, and then store the result into a core variable I. And then you can use I, let's say to say if I crossed a certain threshold, then state is a Boolean and is now true. And then you have full control flow, and then you can do if-then control flow on this state variable, for example. And if it's true, then you play some other pulse. While some error syndrome is 0, you do something. And you have more control flow. You have for loops, as I said before, for each case, switch case, and so on. And so basically you can generate any sequence that you can think of that runs indefinitely. So there's really no constraints I've never encountered in AMO, at least on the memory of inside the pulse processor, because all the pulses are generated parametrically. And I will show you that. I mean, this is easy to say, but not so easy to do. And I have some real live examples I took yesterday. I'll show you. So just to conclude on this slide, absolute timing control. All the signals that are coming out here from all the channels of the OPX or OPX system, if you buy more than one box, everything is timed to the nanosecond. And the relative timing is controlled on the nanosecond, so you can send out one pulse, wait 4 or 5 nanoseconds, and then send another one. And everything is aligned, and it's easy to do so. It's easy to implement. So let's show some real live examples. So this is a screenshot from my oscilloscope. So this is a real QA program. This is the syntax with program as hello QA. I'm going to reset. I'm going to play to an element which is I called AOM1, just to simulate signals going to an AOM. And I'm playing this pi pulse. It's just a constant pulse with a length of 40 nanoseconds. And so that's it. That's what it does. It sends a 40 nanosecond pulse. The carrier frequency of this AOM1 is 80 megahertz, typical frequency for AOMs. And that's it. So that's another important thing in a control system. It's easy. It's very easy to do very simple things. It's important because there are some systems out there where from the moment you open up the box and you connect it to your lab, it can take months before you can do Rabi flopping. So this is unacceptable if you want to work with a reasonable pace. There's a lot of pressure to perform these days. So simple things are simple. If I now use 2 channels, I reset the phase just to start, from a pure cosine. I do exactly the same thing on another channel, on a separate channel coming out of an OPX, and so you see that the 2 channels are completely overlapping here. And so each one of these play commands, because it goes to a different element, it's a separate thread. Okay, so so each one has its own time time vector, if you want time base. If you want the second pulse going to AOM2 to start after the first one has finished, you need to align. So this align needs to be in between the two play commands. You need to align the two elements. Okay. Again, the align needs to be in between the two plays for this type. And so in such a way, you're telling the pulse processor, okay, after you've finished playing this AOM1 pulse, make the t equals 0 of the AOM2 element here. And as you can see, by doing that, the two pulses come out phase coherently, because we've reset their phases at the beginning and we're not resetting it after. So the numerical oscillator, is common mode for both, and the pulses come out with 0 dead time, really 0 dead time, and phase coherently. You can do also ramps, right? You don't even need to generate a pulse. You don't even need to define a pulse. You can just say how many volt per nanosecond do you want to ramp a certain signal and what the duration of the pulse is. And then you can easily generate ramps. You can also generate chirps. So AOM2, just like AOM1, was here set to be 80 megahertz. And here I'm chirping it at a rate of 1 megahertz every nanosecond. Okay, so at the last 40 nanosecond here, the frequency is chirping rapidly. And this is we're coherently evolving the phase, right? So it will be phase coherent with the previous pulse, and everything sticks, and there's no dead time. And this is really the code that is being executed. I'm not hiding anything here. And because everything is parameterized and it takes basically no memory, there are very few numbers here that describing what's going on in this oscilloscope tray. So the 80 megahertz carrier frequency, that's one number. Then the duration of these pulses, you're just telling the pulse processor just run this frequency for 40 nanoseconds. This ramp rate, it's just a number, and this chirp rate and the amplitude, original amplitude. That's it. There are 4 or 5 numbers describing this whole waveform. So now if I want to, instead of making very short pulses, 40 nanoseconds is the time step here, I can make very long pulses. I can change the duration of everything here from being 40 nanoseconds to being 40 milliseconds. And it will take the same amount of time to compile and run. We didn't add any more information to the script, to the sequence. We just changed the duration to be 40 milliseconds. This is in steps this is in units of clock cycles. So it's in 4 nanosecond steps. So we have 40 million nanosecond duration, which is 40 milliseconds. And it runs straightforwardly, and everything will still be phase coherent. If I would zoom in here, you would still see, the waveform with no dead times, completely phase coherent. And so this allows you to generate, ramps and chirping and envelopes completely arbitrarily on any time scale. So it can be tens of nanoseconds, can be tens of milliseconds, and it can be tens of seconds because the thing runs on the fly. The waveforms are generated on the fly, so there's no need to store the waveform. Again, here we have a Gaussian. I replaced this ramp with a Gaussian waveform. This Gaussian waveform, I gave the samples for I think for a 40 nanosecond envelope, but now I'm stretching this to 40 million nanoseconds, and it's on the fly performing this third order Lagrange interpolation and outputting a Gaussian, which is 40 milliseconds long. So I think this should convince you that at least standard laser cooling operations, and also I think you start to see gate operations are very easily described and executed using the quantum orchestration platform. Okay, don't hesitate to ask questions in the chat. I'll take a look from time to time and answer if there's something that isn't clear. Another capability that is important for all QPUs, but for Rydberg maybe in particular, is the capability to do dynamic routing. So all the signals you saw before, all these Gaussians and ramps and chirps, they can be output to any analog output ports that you want, and they can also be summed. So this is a representation of the 18 different cores that you have, pulse processor cores that you have in a single box. And so you can generate one waveform from this core and a second waveform from this core and another one here, and they can be split and combined on ports. So if you have an analog output port, you can have all 18 processor output signals to it, and they will be summed at the output. A core can switch to output to different output ports in real time. One core can be split into 2 or more, so that you can generate, so that the same waveform can go to 3 different or more, or all 8 or all 10 ports. And you can decide on this switching and routing on the fly in real time. So there are many use cases for this. So first of all, we will see in a moment that to do atom arrangement, for example, it takes a lot of pulse processors because you want to be able to control the amplitude and the frequency and the phase of each individual tone in the atom arrangement and in the addressing sequence. And so it takes typically most cores in a single box, but then after arrangement is done, or before arrangement is performed, you can reroute these pulses to do other things and output to other ports. So for example, you might have analog output 1 and 2 drive the AOMs or AODs that are used to do atom arrangement or addressing. And once you're done with that, and you maybe want to drive a different AOM or AOD, you can divert all the pulse processor cores to do other operations, and you can do that on the fly in real time. So this dynamic routing capability is very important. Another use case is that you might want to have one core that is dedicated. For example, this is something our users are doing. One core is dedicated to keeping AOM warm. So simply playing an RF signal that is out of band for the AOM. And so whenever you're playing something to this AOM, fine, play it. This light green and pink and yellow waveform. But when you're not playing, please play this blue one. Yes, so there's a question here. Coherent pulses between 2 boxes are totally possible. So whether you buy one or more boxes, they're connected, and there's data sharing among boxes. And there is some additional latency, but it's very short. I think it's about 100 nanoseconds. But anyway, it's all known and calibrated. So absolutely, you can generate coherent pulses between 2 boxes. You can have one signal come out of output port 1 here, and another one from output port 1 in another box, and they will be aligned to the nanosecond. Yeah, so this will allow you, for example, to keep AOMs warm. So while you play a waveform, you play it, and the moment you stop playing it, you can switch on this blue pulse processor core that will just play out of band to the AOM and keep it warm. 0 dead time, switching in between the 2 pulses. Yes, and it's also phase coherent, but in this example, it's not that important. Okay, so how does it work? So you get 1 or more boxes, and they're connected together. There's some data sharing cabling, common clocks. If you're buying more than one, you have a reference clock that is shared among everyone, so that we can align and calibrate all the different channels. In each one of these boxes, you have a pulse processor and an RF front end. Then you have a server So in the new version, the server is inside the box itself, so you don't have an extra box. It will be inside. And then client computers are connected to the server and uploading jobs, basically. So you can have in the one or more boxes in your lab, and you can have as many students as you want connect to the server, upload their jobs. The server does the compiling and then and does the job queue handling. So we have a job queue. We're really a cloud-based company. We're providing kind of quantum processing cloud services. So you can have 2 or more users all work on the system in parallel, executing jobs, and then the experiments will be interlaced or executed based on the job priority and so on. You can also have one box because it's a multi-core processor. You can split the box into 2 or more parts and say, okay, channels 1, 2, 3, 4, and input channel 1 and digital outputs 1 and 2. They are reserved for experiment number 1, and output ports 5, 6, 7, 8 are reserved for a different experiment. And then 2 different students or 2 different operators can run completely parallel operations on the same box and not even know that the other one exists. So this is also very useful if you want to use some of the OPX channel to do, I don't know, spectroscopy or laser locking. Some clients, some customers want to do that to have the flexibility to change some locking parameters, for example. So you can do pound river hall with the OPX. We have code for that we will give you freely, of course. And so you can stabilize a laser and do pound river hall with the OPX. You will have a bandwidth of several hundreds of kilohertz. And I will show an example of that in a moment. So yeah, you're connecting from the client and you're executing on many different QPUs that you might have in the lab. And yeah, and each one of those is a quantum machine instance. That's the name of the company. And then this allows you to abstract away basically all the nitty-gritty details of all the waveform generation and the pulse level control of your quantum processor, and allows you integration with software, with things which are exist much higher up the software stack, such as Circ or Qiskit. We're in collaboration with Q Control to work on optimal control pulses, and you can download QA scripts and sequences from our GitHub, or download QA code from some researcher, and it will just execute seamlessly. So having such a platform that is already built for you has the added advantage that you're automatically connected to a community which is much larger than what you're doing, and all by yourself. This is an advantage that you won't have if you decide to build your own. You will have to write your own integration tools with all the higher level software stacks. Okay, so each box has 18 processor cores, full dynamic control on cores routing. I've shown you that. You can add more OPXs, and sync and clocks are seamlessly taken care of. So it will, in software, a stack like that will appear as if you simply have 60 analog outputs, 60 digital outputs, and 12 analog inputs. So 60 analog, 60 digital, and 12 analog inputs. To that, you can connect products that will come out soon, next year. So camera link interface, we will have a device that does the image processing and then stores the results of the image processing into QA variables, so that you can take images of your atoms or ions and define that image processing algorithm. And the hope and what we're working on is to have very low image transfer, image processing, and data transfer to the OPX, trying to shorten this as much as possible, with, of course, a vision towards quantum error correction with cameras, which people currently think is possible to do. You can also interface with single photon counters, single photon detectors. We have a unit for that as well. Photodiode arrays are also supported. You can connect them directly if the output is digital. You can connect them directly to the OPX, and so you have access to all the readout channels that are typically seen in superconducting and in AMO labs. Up-down conversion up to 18 gigahertz if you want to do gigahertz stuff. 6.8 gigahertz for video, 9 gigahertz for cesium, not a problem if you want to make excitations, global excitations in the microwave regime, for example. And something that is very important and we take a lot of pride in is our exceptional support and documentation. So documentation is extensive. Every feature, every function comes with a detailed explanation of all the parameters, typically some example code. We're heavily implied in that. Every physicist in the company writes some documentation from time to time. We're always making sure that whenever we answer a customer, that this answer is then turned into some post in the documentation or something like that. And support is beyond documentation. We are a very hands-on company. So we like to say that we are as hands-on as you allow us to be. So typically before a customer buys a system, we meet with him, we understand his physics, we will write a few sequences so that when he installs the system, he's up and running. So typically an installation takes several days, where we will meet beforehand and discuss the particular sequences that you want to run. We will write code for you. We will come to install and make sure this code executes. So if you have nothing in mind in AMO, we typically finish a 3-4 days installation, by having Rabi flopping, Ramsey, spectroscopy, all these scripts already running, so that you can, you can hit the ground running basically and not have to, be stuck from day one. After we finish the installation, we have a hotline kind of on Discord, a chat platform where you can ask questions. We're typically answered within an hour. We're trying to build a community. We're building a community around Qua, so you can also chat with other users. They don't have to be, Rydberg AMO physicists. We have, randomized benchmarking code is common to all platforms. You just change the shape and some details of the implementation. But you can see chats which are very interesting on the Discord channel between somebody building superconducting processors and somebody building an ion-based processor, and they're talking about the details of implementing randomized benchmarking, for example. So support and documentation is a very strong part. You will get responses very quickly from us, and you will engage with the physicists. So we really are a company of physicists for physicists.